Okay, so let's start. So turn on video. So for students who turn on video, I will give the 0.5 the bonus credit for your quiz score, and 1 point if you have you asked questions. Yep. I haven't added those points yet, but yeah. Okay, and so Jordan and Andrea and Ryan Brianna. Lex Dalbo. And Neil and Grant. One, two, three, four, five, six, seven, eight. 1, 2, 3, 4, 5, 6, 7, 8. And Sakina. Okay. So at first, I want to discuss the one question I got during the office hours. I will share the screen first. Yeah. Oh, first the quiz 11.4, the Avalon dataset is only available in CSV format, and depending on your web browser setting, you cannot download it. So I added the zip file. So if you have already access to the problem and cannot download the data, that you can finish the quiz once, then you can reload the quiz, then you can also download it as a zip file. And I also increased the number of attempts allowed into 3. So you still have the 2 times to answer the question. Okay, so I got a question about the missing values in the dataset in your final project. So what to do if we have missing values? So suppose we have maybe 100 observations in the data set and maybe 10 variables, and maybe some variables do not have any missing values, but some variables have maybe 5 missing values or something. So that is a typical situation. And there are several ways to handle those cases. Maybe I would say 100 sample unit. So the easiest way to deal with NA is just discard all lines with at least 1 NAs. With 1 or more. So if you have many sample units and only a few observations are missing, for example, in total, for this 100 by 10 table, you only have 2 observations are missing, then maybe you want to discard the lines with 1 or more NAs. And the second way to deal with is imputation. So typically, they impute the median value. So if we have observations such as this, okay, so we have variable X and we have 5 sample units, C1, C2, C3, C4, C5. And if the second observation and fourth observations are missing, then you can just plug in the median value. So that is one way to deal with. Yeah, there are some other ways to impute. For example, based on other variables value, we plug in some more plausible number for imputation. So that is another way, and there are many imputation methods, but the most basic method is impute median. Maybe mean is also possible, but usually the median is more robust against outliers, so the people use median. But if you plug in median, we have some statistical problems. Probably the most serious problem is maybe the missing values have some tendency, and if we impute median, we have some trouble in estimation. For example, suppose we want to identify the kids who have trouble to study mathematics, and we make a survey and ask them the most recent math exam score. Okay, and if score is good, all students will answer their scores, but if score is bad, maybe some students don't want to answer. So in such a case, the missing values have some tendency. So in such a case, that we have to deal with missing values as somewhat useful information. And to deal with that situation, we can do this way. So in addition to original variable x, we add another variable. This is the indicator variable for missing values. So yeah, you can just tentatively put median value for x, but also we introduce this indicator variable for missing values. So sample unit C2 and sample unit C4 have missing values for x. So we add another variable, which is an indicator of missing values. Then if this coefficient, if you fit the data and if we got the coefficient of, for example, negative 0.2, then that means the missing values have some negative bias. So actually, if data is missing, the expected number is less than the median value of x for other observations. So this is more comprehensive way. So it really depends on the case, which way you want to use. If missing values don't have much information, then you can just go with the first or second way. And if you want to do more detailed analysis about missing pattern, maybe you can do this. Yeah, also the imputation, artificially make the data. So that also underestimates the standard deviation of the estimates. That is another possible problem. But anyway, so you can do it in any way, but there are several ways. Just I want to introduce several ways to deal with missing values. Okay, do you have any questions about final projects or any the quizzes lecture? Okay. Then we go to chapter 11. Oh, this is the different class, chapter 11. Yeah, so today's topic is the model search for multiple linear regression and the model diagnosis for linear regression, multiple linear regression. So first one is the model search. So in multiple linear regression, usually we have the several potential predictors. So we have continuous variable y, and we have x1, x2, x3. Maybe we have x20. We have several the potential predictors, and we want to get the best set to predict y. Maybe the x2 and the x17 and the x19 are actually the useful variables, but the other variables are not useful. Then we want to get this model as our final model. And how to find this best combination of predictors, that is the first topic. And what does it mean for the best model. So the best model means sometimes best model for prediction. So suppose we have 100 observations, but we observe maybe 10 new observations, but we don't know the Y values. Then what's the best way to choose the model? So that is probably the most typical problem. And sometimes we want to see the true predictors of the model. So at least in simulation setting, we can see, what is the true model. For example, if we generate Y, based on X2 and X17 and X19 and some noise, then we know that these three are true predictors and the others are irrelevant. And how to identify this true model. So that is another question. And these two are slightly different. So yeah, usually for the first objective, the more variables may be included. So suppose that's the situation that there are 10 variables, 10 predictors that possibly improve the prediction, but yeah, so maybe, yeah. So suppose that the 10 variables, yeah, maybe the better way to put it is if you include the 10 more variables, the prediction gets slightly better, but each of those 10 variables is not significant at all. So what is our action? We just discard all of 10 variables, or we adapt all the 10 variables. So we have to decide either way. But for prediction purpose, usually it's good to include all predictors, because usually adding the additional predictors are not that harmful. So if we have those 10 variables have potential to improve the model, usually including those is better. But if you want to identify the true model, then probably you want to be pickier, then we want to discard those variables. That is another possibility. So we have the slightly different objectives for these two. Most of the time, maybe you want to improve the prediction model, but sometimes you want to focus on true model. Yeah, but the true model is usually unknown for real data set. So the meaning maybe not clear for the second objective. And how to select the best model, for example, in terms of prediction accuracy for new observations. And naturally, the try all combinations is the best way. So suppose that we have 3 possible predictors, X1 and X2 and X3. Then we have 8 possible models. Maybe to make it simple, only 2 variables. Then we have 4 possible models. The XY and X2 are included in the model, or only X1 is included, or only X2 is included, or nothing is included in the model. We have the 4 possibilities. So if, for example, X1 and X2 are totally irrelevant to Y, then these 3 models just add unnecessary noise. So that means that this is the best. But we have 4 possibilities. And if in general, if we have the p variables, then we have 2 to the power p combinations, because we have to decide whether X1 is included and also whether X2 is included or not, and X3 is included or not. We have p variables. So in total, we have 2 to the power p combinations. So if p is equal to 5, the 2 to the power 5. So we have 32 possible models. If 10, 2 to the power 10. So the 1024 combinations, p is equal to 15, then we have to multiply 10. So that we have about the 32,000 combinations. And you can see that if p is large, this method isn't really realistic. Probably up to p is equal to 10 is fine, but if p is equal to 20 or 30, then certainly you cannot do that. So another way, maybe the second best way, is the stepwise procedure. So stepwise procedure may have the two patterns. So one is the forward selection. We start with the smallest model, maybe model with the intercept. Then we add one variable at that time. So yeah, so suppose that we have 10 possible predictors, x1 to x10, and the forward selection means that we try the minimal model at first. Then next step is we try y on x1 and the y on x2, y on x3, and so on. So we try the 10 combinations and choose the best one. Suppose that the y on maybe x7 is the best. Then the next step is we include x7, but we try another predictor, y on x7 and x1 and x7 and x2 up to y on x7 and x10, and choose the best one. You know, best means the best in with some criterion. So we can choose some criterion, and we will discuss it later. But we choose the best one in terms of some criterion. Maybe, okay, so the x3 is the best, and maybe I should say that the also the smaller model is better. That is possible. So we consider just the model with x7 only. Then we continue. So next one is x7 and x3 and another variable. Y on x7 and x3 and another variable. Y on x7, x3, and x10. And also that we consider x7 and x3 only. Then we increase the number of predictors until the previous model is the best. So that is the procedure. And how many models we have to try? At first, we have, okay, so one model. This is almost trivial model. And we have the 10 possibilities here, right? And in the step 3, we have 9 possibilities. You know, this model has already fit. So we have 9 other possibilities. And step 4, we have 8 other possibilities. So if finally all variables should be included, we have actually so we have to try. So 1 plus 10 plus 9 plus 8 plus up to 1 models at most. So this is, okay, so summation of 1 to 10 is 55. So this is 56 models. But if we fit all combinations, then 2 to the power 10 is 1024. So this is much larger than 56. So this selection method is much more efficient than trying all combinations. So this is the forward selection. But of course, sometimes, the x7 plus x3 plus x2 is the best model. Then actually, x7 isn't necessary. That is possible pattern. Okay, so if we have to select one variable, we have to select x7 first. But it's possible that if we include x3 and x2 as well, x7 is no longer needed. That is another possibility. So this does not guarantee to reach the best model, but still, in the most case, it reaches a reasonable model. So that is the forward selection method. And the backward selection methods is another way. So the other way around. So the first model is the full model. So we try y on x1, x2, x3, up to x10. we fit on all?
If you guys are wondering, I don't have a plan for the final project. Does anybody else have a plan? Or maybe someone can inspire me?
Sorry, I just got back. Where did Professor go? Did he?
I think connection went out.
Yeah. And I would just say do something you like for the project. Like I'm just gonna do basketball because I like basketball, and so that it, like make the project more so fun, opposed to looking at it like it's supposed to be a project. So do something you like.
Yeah, that makes sense. I would say like I'm just trying to do something where I can get a bunch of data on, because like surprisingly there isn't much data out there, to be honest. So like I'm doing mine on life expectancy. There's a lot of data out there. So
I mean, I like food. I just don't know how to make that into a final project.
Someone gave me the option to try, like, I might not do this, but like look at the life expectancy of dogs, or like the reasons of death for dogs based on like the season. So like in holiday time, like there's like a higher percentage of dog deaths, like because of like the like chocolates and stuff, like in Halloween there's like more candies and stuff. So yeah.
That's a really cool conclusion.
Yeah, that was just an idea someone gave me. I don't know if it's like if there's even any data for it, or yeah.
I mean, if you like food, you could do something about like agriculture or something. I also have no idea what I'm doing. I was looking into like weather data and like it's so confusing. I'm like, there all these like codes for all the data, and I'm like, I have no idea what this code means, and there's nothing like explaining what the code is. It's so confusing.
honestly, I found that the 3 examples that he gave were really helpful in terms of how I should approach it, like how many factors or whatever. That's really helpful too. So I was just gonna like follow that.
Back to the quiet awkwardness.
How long do we stay here before we start reaching out, being like, what do we do now?
5-minute rule. If he's gone for more than 5 minutes, we get
It's
to leave.
already, I think it's been more than 5 minutes already.
I think it's been 3. So we wait 2 more. Actually, probably 10 minutes. We'll give him 10 minutes. At least.
Yeah, I was actually talking to someone at my door, and it got all quiet. I'm like, oh, are we in a breakout room? So I come back. I'm like, no, everyone's just standing here. So yes. Oh well.
I thought the same thing.
Low key, this is a breakout room. To be honest, I feel like this is what I do in a breakout room.
I agree. How are you guys feeling about this class? How's it going for you guys?
I think the final project's just gonna scare me a little.
Yeah,
The whole grading as well.
yeah, definitely.
Oh, the professor.
Hi. Sorry, the internet, my internet connection has some trouble and everything is down. Sorry. Yeah. Yeah, sorry about that. And I will share the screen. Okay, so I think that you have probably finished listening the forward selection part, right? So I will start the backward selection from now. Okay, so I got one question maybe. Yeah. Great breakout session, everyone. Yeah. Sorry about that. Yeah. So the backward selection, they will start with the full model. So y on all x1 to x10. Then we make it a little one smaller. So the second step is we compare the y is equal to x1 to x10, x9, and the x1 to x8 and x10. So excluding x9, and y is equal to x1 to x7 and x9, x10, and so on. And of course, also this model as well. So say this model. Then we choose the best model. So suppose that the best model is y on x1 plus x8 plus x10. Then we reduce the number of predictors once more. So there may be x1 to x8 and the x1 to x7 and x10, and so on. And also this model as well. Then until the model, the reducing predictor does not improve the model. So then we stop. So that procedure has also have the same number of trials. So first we try this model, and the next we drop one of the variables. So we have 9 possible ways, and then 10 possible ways, 9 possible ways, and so on. So in this case, we still have the 56 possibilities we have to try. So that is the case. I got another question. What is the possible downside to just include all possible predictors? Yeah, so that is basically adding the unnecessary noise. So that is our problem. So yeah, for example, yeah, I think it's a little hard, but think about the maybe 5-year ahead prediction of something, the temperature or something. Then if we mistakenly include the increasing trend, then 5 years later, that prediction will be the very high, unrealistically high, for example. So if we include unnecessary predictors, then potentially for new observations, the prediction may be worse than including that variable. Yeah. So, the basic principle is if model is unnecessarily complicated, that model is worse. So simpler model is better. So that is the basic principle. And actually, the data tells the simpler model is better for out of sample predictors. Yeah, that's a very good question. Neil? Yeah, so that's it. So yeah, so those are the stepwise, the selection. So the first one is forward selection, and the next one is the backward selection. Sometimes we combine the both methods to optimize the predictors. So that means, suppose the we have the 4 possible predictors, maybe the 3 possible predictors, just as a simple example. The including everything is the largest model, and the dropping 1 variable is next largest, like this. So this is one model, and this is another model, this is another model, this is another model, and x1 only, this is another model, x2 only, this is another model, and x3 is another model, and the nothing is another model. And we have some connection between these two, so maybe this one is larger than this one, x1 and x3 is larger than this one, this one, this one, this one, this one, then maybe this. So the forward selection is that we only go up the model, maybe this way and this way or something like that. And the backward selection is that we only go this way, so go down. But the both ways means that we can go up and go down every time. So I think that for 3 variable case, probably that's not really possible, maybe, but yeah, maybe still, we start with this and we go to this and go to this and go to, yeah, I think it's not possible for 3 variable case, but sometimes we go down, then the model gets better. So if we can go up and go down in either way, then actually model can be slightly better. So both backward, forward selection, that is another possibility. I think that for 3 variables, it's not probably possible, but more than 4 variables, such procedure is possible. And maybe if we go both ways, maybe it takes much longer time to converge to the best model, but still, it may be slightly better. So that is the forward selection and backward deletion and both. And and I got another question. So how might we try all possible combination of models in R if we don't want to explicitly write out every combination? Actually, yeah, we have to explicitly write all possible combinations. So maybe if we have 10 variables, then we have to make a for loop with the 10, we have to make 10 for loops, nested for loops to do that. So it takes time. Yep. So our ballpark estimate is maybe about 10. So more than 10 variables, it's probably not realistic to try all combinations. Yeah. Maybe, 11, 12, that's possible, but probably 17 or 18, not possible. Yeah, I got the question from Parser. Yeah, just before I forget, I want to check the attendance, so just a moment. We have 20. Yep. Okay. Yeah, so now we want to discuss what criterion to choose to find the best model. So there are several criterions, and maybe you can come up with the adjusted R square, because adjusted R square penalize the large model. So if P is large, P is the number of predictors, the P is large, the adjusted R square gets slightly smaller. But the people know that the adjusted R square tends to choose the too many variables, so that actually the future prediction performance is negatively affected. So the adjusted R-square isn't really a good criterion. And I think the most popular criterion are these AIC and cross-validation. So AIC, Akaike Information Criterion, that chooses the optimal set of predictors for prediction if n is large and n is sample size. And AIC is defined by the 2p times, the 2p minus the 2 times log of likelihood. So here the likelihood appear. And the likelihood, of course, larger is better. Larger likelihood better. Better. So that means the negative 2 times log likelihood. So smaller is better. So smaller is better. And also the p is the number of predictors. So smaller number of predictors makes a simpler model. So smaller is better. So smaller AIC is better. So if p is larger, then we have more predictors. Usually likelihood is larger, but if p is large, the first term becomes large. So we cannot get the small AIC. So the model with the minimum AIC is best. So that was proven by the Akaike in 1973 paper. And that is the simplest method if we have likelihood function. And another way is the cross-validation. So cross-validation is a simulated method. So it divides data into the 2 data sets, and maybe we have data set D, then we make it D1 and D2. We separate D into the 2 sets. And we use the one set, D1, as so-called training set. So we fit the model only with D1. And we calculate the error size based on D2. So basically, we mimic the actual situation that we have training data set to fit, and we have test data set to measure the performance. So basically, we pretend as if the D2, the response value for D2 is not available. But if we randomly, divide dataset D into 2 pieces, that has too much randomness. So we do in both ways. So we use D1 to make a model, and we check the performance with D2, and we do the other way around. We use D2 as the training set to fit the model, and we test the performance with D1. So we do both ways, and we take summation of the total error size. Then we can see which model is better. Yeah, so that's the cross-validation. So what do you think? The AIC and cross-validation, which becomes more popular these days?
AIC?
Yeah, actually not. Yeah, so the AIC looks more advanced, right? So, but these days, the cross-validation is more popular because the computational power, we have more computational power. So the problem of cross-validation is computational power. So we have to spend a lot of time to do that, because in this case, it's fine because we only have 2 data sets, but actually in general, cross-validation have k-sets. So, sorry. Sorry, maybe I should have explained this one, but in general, that we have the k-fold cross-validation. So for example, the 3-fold cross-validation. So that makes data set into three subsets, D1 and D2 and D3. And we use the 2 of these data sets as training set. And we use the last one as test set. And we could repeat this for other combinations as well. So training. So we have yeah, sorry. In general, cross validation have the k-fold, and that means that we have this one. Three times, and the first time that we use D1 and D2 as training set, and the second time we use the D1 and the D3 as the training set, and the last time, at last, we use the D2 and the D3 as training set, and this is test set and this is test set. So basically, we fit the model the 3 times, and generally speaking, the best cross-validation is n-fold cross-validation. So that means that we divide the n observations into n data set. So just leave first observation, leave the last observation first, then we use the remaining n-1 observations, then we test with the last observation, and we repeat that n times. So that makes a lot of time, and this is computer intensive. So that's why the people are not, it is not realistic to use the n-fold or the k-fold cross-validation in old days. But these days, we have more computational power, so we can do that. And also, the cross-validation has the benefit because we don't really need the likelihood function. So linear model is fine, but if we have more complicated model, maybe these days neural network, deep learning, so we cannot really calculate the likelihood function. So the AIC is too complicated to do that. So the people use more cross validation. What is the value of the CV gives you in terms of predictive power? It is like an R square. Yeah, so cross-validation, usually the most popular criterion is the summation of actual yi hat minus yi square. So the sum of squared residuals. So this is probably the most popular criterion. So we minimize the sum of the squared residuals given by cross-validation, yes. Yeah, so generally you can choose different criterion. For example, maybe you can use the summation of absolute value of yi hat and yi. That is another possibility. So we generally have the error function, but this is most often used, probably because it corresponds to the normal likelihood. So if SSR is minimized, then basically the likelihood is minimized based on that heuristics that we use this. Yeah, so cross-validation. And there are some other criterion. The one popular one is the Schwarz-Bayesian information criterion. So this is kind of similar to AIC, but that we replace these two by, I think, the log of n+1. Log of n+1 times p minus the 2 times log likelihood. So we have the larger penalty than AIC. So people claim that this criterion is better to choose the true model. So if you do simulation and you do model selection by AIC and Schwarz BIC, then the Schwarz BIC is better to identify the true model. I got another question. Is it necessary to include model selection in our final project? Not necessarily. So if your objective is to choose the best prediction model, then it's good to choose it to do model selection. But this is statistics class, so the significance of predictors or identifying whether relationship between y and x is significant, those are more important objectives. So you don't necessarily have to include the model selection. Yeah. So if you will take the data science class the next semester that start 5820, maybe I have to advertise it. This is more forecasting oriented class. So the more projects predict something, but the for 5030, it's really about statistics. So you don't really have to include it. Of course, you can include it if you would like. Yeah, that is a good question. Yep. Yeah, and cross-validation, usually the default in R package or other Python package, usually we have the 10-fold cross-validation or 5-fold cross-validation. So that is most typical cross-validation. So divide data set randomly into 10 pieces or 5 pieces. So if we divide it into 10 pieces, we fit the model 10 times. Then we calculate the error size. That has some randomness because we have to randomly, separate the data set into 10 groups. So that makes some randomness. Yeah. Any other questions so far? That's fine. Okay, so now that we have the R code to run the model selection, and that this is by AIC. And we use the dataset from the library ISLR. So this is for dataset. The cyst fiber dataset. And yeah, you can see the description of data. So this is the, I don't know. So basically we have the data set for lang function, and the PE max is the response variable. And other variables are possible predictors for this lang function. So age or sex or height, weight, BMP. I'm not sure what is BMP, but these variables can explain the PE max. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 possible predictors in this data set. So yeah, we want to fit the model. And yeah, so we want to fit the model, but we want to do the model selection. So in this case, we have 9 possible predictors. So possibly you can try all combinations, but here I would like to use the stepwise procedure. And we have some errors in this slide. Actually this line should be included in the previous page. So I fit the full model, LMF. This is the PE max on other 9 variables, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the result of this model is here. So we have 9 predictors here, and coefficients, age and sex negatively affects. Sex, maybe we have indicator variable, probably the male and the female, and probably the male is 1, maybe. So the male has the lower lung function in this data set. And if the person is older, then lung function is lower or something like that. Then we have these variables. But when we see these t values and these p values, actually nothing is significant. So it sounds like nothing is useful in this model, but actually not. Because if we see the R square value, we can see that about 64% of variability in P max variable is explained by these 9 variables. So in total, probably this is useful model. And you can see also the P value for the F test. The P value is 0.03. It's not super small, but still it's less than 0.05. So overall, these 9 variables are useful to explain the lung function P max. Yeah, also even adjusted R-square, the 42% I explained by the model. If nothing is useful, basically adjusted R-square becomes around 0, but still this is the 0.41. So 42% of variation is explained. So probably the sum of the variables are useful, but the model is too large to find which variables are significant. So we do the stepwise, the procedure, and the default is backward. So you can check the stepwise function in R and see if what's the situation. So the direction, oh, sorry, actually currently the both is the default. So this is both is default. And if we want to run the backward selection, we have to specify the option direction is equal to backward. Or direction is equal to forward to make forward or backward deletion algorithm within step function. Oh, here is another small question. So which is faster, the backward deletion, forward deletion, which is faster? What do you think? You can go back to the algorithm. So forward deletion and the backward deletion, we have in total the possible maximum patterns we have to try is the same, 56. Backward, forward. Okay, so the person said backward and one person said forward. And actually the forward is faster because the most models are smaller. You can see that these models are small. Just the fit y on x1, y on x2. This is simple linear regression. It's faster. And if backward, then we have to fit all variables, so 10 variables. So that takes time because the fitting this means that we have to calculate the inverse of 11, the inverse of the matrix with 11 by 11. So that takes more time. So yeah, of course, it depends on which model is the best. If the true model needs the 9 variables, possibly the backward is faster. So it really depends on the situation, but the generally forward is more efficient way. I got a question. So won't you also need to do that for forward? So yeah, if final model is very large, of course, we have to try all. But suppose that the final model have only 5 variables, then forward selection have to fit the model with at most 5 variables. But the backward deletion method, we have to try a model with 10 or 9 variables as well. So the forward is usually faster. Of course, it depends on the situation, but the more likely forward is faster. Yeah, so if you have too many variables, maybe you can try forward selection. But the backward deletion, I think probably the people think that it can reach the better model in more cases, maybe. So that's why sometimes people try backward. Yes. And this is the selection by AIC. So AIC is used for the selection criterion. Yeah, and this is the table. So basically, this is the null model. We don't have any, sorry, this is backward. So both selection, but the both ways the default is the full model. So you can also specify the starting model and the largest model and so on. But it starts with the full model. So the full model has AIC of 169.11. And if we remove sex, then AIC becomes the 167.2. And if we remove TLC, 167.34, and so on. So AIC improves by about 2. And remember that if we add entirely useless variable, AIC gets worse by 2. So that means that this sex is almost entirely useless variable. So we should remove it. And we can continue these procedures. And now we only have 1, 2, 3, 4, 5 variables, and that we exclude height, then the AIC still gets smaller, almost by 2. So the height is almost useless variable. And after we remove height, then we have 4 variables remain. And and actually if we remove one more variable, then AIC gets always worse. So you remove RV, slightly worse. If we remove weight, the AIC gets larger by 16. So suddenly we need these 4 variables. So this is the final model. So the 4 variables are included. So this is the result for the best model. We have the 4 predictors, the weight, BMP, and FEV1 and RV. And actually, for the best model, this weight and the BMP and the FEV1, so these 3 variables are statistically significant. And the last variable is not statistically significant, but the t-value of 1.5, p-value of 0.14. So it's not significant, but somewhat large, 1.5. Yeah. So that's the situation. Yeah. In another class, actually I ask in the midterm whether September anomaly in the stock market is significant or not. So people say that in September stock market return is significantly worse than other months. And actually this year September has the very large drop in stock market as well. And we tested it, and actually the t-value is about -1.5. So -1.5 is a kind of not statistically significant, but the people can recognize it may be worse or better. Yeah. So in such a case, AIC is pretty conservative method, so it can include the variable. Yeah, I got a question. So is there a consideration outside of computational cost that would make you not use both? Actually, probably no. Yeah, you can do both ways. Yeah. Yeah, probably no. Yeah, I believe that's I don't know. Yeah, I think probably no. Yeah, you can do in both ways. It have higher chance to reach the optimal. Oh, you are Jordan Rippey. Yeah. Yeah. So if you run this procedure, actually all intermediate results are displayed on screen. So if it's annoying, there is an option to suppress the output. That is, I think, the trace option. So if you specify the trace option is equal to 0, then suppress output. So probably you will see only the final output of the best model. Especially if we have 20 or 30 variables, you don't want to see intermediate results. Yeah, and okay, so the final model, we have the multiple R squared of 0.61 and adjusted of 0.536. So the full model, the adjusted R square 0.419 or something. So it has been improved, and the p-value actually gets even better. So if we remove the unnecessary variables, then test result become clearer. Yep. And model diagnostics. So we don't, yeah, and the model diagnostics is the probably the most important part if you take statistics courses. So for example, the running the stepwise selection, that can be done by any person. So just the right step of the linear model. But the statisticians, they see if the model assumptions are appropriate. So that is probably the strong part of learning statistics. And once you fit the model, then we have to check the residual plot and the QQ plot. It's similar to simple linear regression, but those should be done. So this time we have multiple predictors. So we plot the epsilon j hat on y-axis against each predictor on x-axis and see if any pattern indicates the dependence of epsilon j's. And for time series data, also you can try to plot the epsilon j hat against time index to see if the adjacent errors, epsilon hat t and epsilon hat t plus 1, are related or not. Yeah, so we have to do this for each predictor. So maybe I would say each predictor on x-axis. And the QQ plot is just the residual size, so the same as simple linear regression. So first QQ plot of this previous one, and it almost has the straight line. So I think it should be fine. So the problematic case is like this kind of pattern. So specific, especially this, the convex pattern. Then probably we have to transform y value. So like the log of y or maybe square root of y. So these transformations are suggested. But this looks good, almost on the straight line. Not exactly, but this is real data. So not the ideal, but I think it's acceptable level. And these are residual plots for each of the predictors. So this is weight and the BMP, the FEV1 and the RV. And the y-axis is the same, they're all residuals. And if we have any pattern in any of the figure, then we have some chance to improve the model. Maybe it's better to put the x-axis here. So this is 0. So and I think that we don't really have any pattern here. So in terms of y value, we don't really have pattern. So it's almost random. So, problematic case is if we have some specific pattern like this, then certainly, the BMP square, there should be another predictor, right? So because we have quadratic pattern. Or if we have larger variation when predictor values are larger, like this, then maybe we have to transform, I don't know, it's not clear, but sometimes we have to transform y. Yeah, so if we have some specific pattern in residuals, then we have to remove those characteristics to get a better model. So at least I suggest the QQ plot and the residual plot. And certainly if you include it, your final project would be better. Any questions so far? And this is just the code for the previous figure. And Yeah, these days the people use RStudio, so you don't really need to save the file. But if you want to save a file as the PostScript EPS file or a JPEG file, then this is useful. So the first one, I saved the QQ-plot, the QQ-norm function. So this makes some graph. And this PostScript function, they save this as a PostScript file. And also, I think the JPEG function, the JPEG function, save it as JPEG, and some other ones. I think the user interface can make you to save it as the JPEG or PostScript if you are using Windows, but the for Mac operation, the Mac OS X, the only option is the PDF file. So if you want to save in a different format, then you have to use this kind of functions, PostScript function or JPEG function. You can specify the several, the size of the file and so on, aspect ratio and so on. Yeah, so that's it. And the last topic to deal with is multi-collinearity. So if multiple predictors are almost linearly dependent, for example, the x1 is almost equal to x2, or maybe 2x1 plus x2 minus x3 is almost 0, or something like that. So then we have trouble to distinguish the models. I mean, we have trouble to identify the model parameters. So that makes basically the standard errors of the coefficients becomes large because the estimate of beta are not really reliable. So maybe the more physical image of this problem is this. So imagine two dogs pull the leash in the same direction. Then it's hard to decompose the force into two forces in your brain. Okay, so if you are walking two dogs, and if two dogs pull the leash in different direction, okay, so this is the dog one. Sorry, I'm not really good at writing the dog, but the dog one and the dog two. Then it's easy to decompose this force and this force. But if these two dogs pull the leash at the same direction, so this is F1 and F2, and if you only feel the total force, it's really hard to decompose this F1 and F2. Right? So that kind of thing happens. Or maybe it's better to say that if x1 and x2 are almost the same, then y is equal to 2x1 plus epsilon, and the y is equal to x1 plus x2 plus epsilon. So these are almost the same model. So we cannot really distinguish those two. That means it's hard to estimate parameters. I got a question. So rather than testing all the predictors in one model, do you suggest splitting the predictors up and testing a couple in many models? Yeah, so I think the answer is kind of yes, if you have many predictors. So suppose that you have the 500 predictors, then probably it's hard to run forward selection model. So probably that you want to reduce the candidates of predictors into like 30 or something. So for that purpose, maybe you can fit the simple linear regression on each predictor. Then you can reduce the possible predictors into small number. Yeah, that may be useful. Yeah, that's a good question. And what happens if this multi-collinearity happens? And yeah, actually for prediction purpose, multi-collinearity is not a big problem because the predicted values may be stable even if each coefficient is unstable. So, if your objective is identifying true parameter, then we have trouble if this model and this model are almost the same. But anyway, the value of 2x1 and the value of x1 plus x2 are similar. So as a prediction model, that you can use either model. So it doesn't really matter. So that is one answer. But if we want to avoid it, for example, you want to identify the true parameter, or you want to see if the parameter is positive or negative, or something like that, then we have some possible remedies. But that is beyond the STAT 5030 material. So one is the principal component analysis. So this is to make a linear transform of predictors to make them orthogonal. And the PCA, the principal component analysis, makes the first transformed vector have the largest variance, and the second vector has the second largest variance, and so forth. So suppose that the image is that if we have similar predictors x1 to x3, then probably one intuitive solution is we take just average of this, right? Then basically we can take the most of the information from x1, x2, and x3, right? And yeah, so that's the case. So this is a kind of the first principal component. This is not equal, but most of the time, if we take the average or maybe weighted average of x1, x2, x3, then it has the most information out of these three. Yeah, so think about the test result. So we have the English test and the Spanish. Okay, so the kids take the test for three subjects: English and the Spanish and the mathematics. Then maybe the overall performance is one good measure. So that is the English, the Spanish, and the math, and we take average. But maybe the secondary information is that maybe some students are good at language and some students are good at math and science, or something like that. So in such a case, maybe x1 plus x2 minus 2 times x3, this may be a good indicator. So this may be the second principal components, or something like that. So we have some method to extract information by using the linear combination of variables. So that is so-called principal component analysis. And the second way to avoid this multi-collinearity is penalizing the size of coefficients. So we have minimized basically the negative log likelihood, or maximizing log likelihood. But we want to minimize this, but also that we penalize the parameter size. So if the parameter theta sub I is large, then we penalize it. Then obtained model, they should have smaller parameters. So then we can get somewhat stable results. So sometimes we use the R theta as the summation of the square of theta i's. Sometimes the summation of absolute value of theta i's. So the first one is called lasso. So this is called lasso. And this is called the rich regression. So these are beyond our course material, but that is another way. I got one question. So if factor x1 and x2 are correlated with each other so closely that they are indistinguishable, then wouldn't they both be equal important to the model anyways? Yes, that's true. So in such a case, sometimes you want to discard one of the variable, just you use x1, or maybe take average of x1 and x2. It really depends on the situation, but yes, so probably it isn't really reasonable to use two variables. So in such a case, probably we have to do something like principal component idea, not really penalized likelihood. And the most, the extreme situation for multi-collinearity is here. suppose sample size is n and the number of predictors is p, and the p is actually, sorry, this is wrong. So if the sample, so sorry, the other way around. So sorry, the smaller. Okay, so if the sample size is smaller than the number of predictors, suppose that the sample size is 100, but the predictors we have, for example, 10,000 predictors. So in such a case, the basically, we have 100 the observations. So the data, so the y is in 100 dimensional space. So in such a case, if we have the 10,000 vectors, always those vectors are linearly dependent, right? So we cannot actually estimate the linear model. So in this case, that we have to use this penalized likelihood methods. Yeah. So we have to fix it. Yeah. Yeah, and such situation often happens. For example, that we think about the image data. So for example, the medical image is one sample, and image is 100 by 100 pixel data, and each dot has some, maybe the grayscale from maybe 0 to 32 or something like that. Then we have the 10,000 dimensional data, and it's very possible that we only have 100 images, right? So in this case, that we have larger p, so the p is larger than n, so we have to do something like the penalized likelihood. So probably that kind of data isn't very appropriate for our final project because it's harder to deal with. Yeah, in such a case, maybe, as another student asked, maybe you can do simple linear regression first, then we can, restrict the number of predictors beforehand. That is another solution. Yeah. Sorry, the lecture has been interrupted, so I didn't have enough time to finish the last section. But next time that we do the more quantitative discussion of this multi-collinearity. Yeah, and the final project plan is due on, I think, Friday, so tomorrow. So submit it by Friday. Do you have any questions? Okay, so if not, see you next.
Professor.
Oh, yeah, sure.
A bunch of us, they kind of had like no clue what they're gonna do for the final project.
Mm-hmm.
So if possible, could you just push it back like a day, like have it due Saturday night opposed to Friday night?
Sorry, but no. If you have questions, you can ask now because we have very tight schedule to see the final project plan. So what part is unknown? So how to select the data set or how to select the models? Which part do you have difficulty to do final projects?
I did mine. It was just I know some people were like discussing about it, so I just wanted to try to ask to see if they could push it back.
Yeah, actually, but this is very tight schedule. So I set it the latest as possible because we are learning new materials. So as late as possible, but I cannot really make it later. So yeah, sorry about that. So yeah, so if you have questions, you can ask today, or yeah, you can email me for simpler questions or set up appointment for tomorrow. So yeah, you can remain online if you have trouble to do final projects. Yeah. Okay.